Welcome everyone. In this video we will derive the formula for charging a capacitor in a RC circuit. Now what is an RC circuit? It's a circuit where we have a battery. Let me draw it here. Where we have a battery, a resistor, that's where the R comes from, and a capacitor, that's where the C comes from. Okay? And the electromotive force of the battery will be epsilon. This is the voltage across each terminal of the battery. So now there will be, let's say, an initial charge of Q naught on the plate. And the left side is positive, the right side is negative. I chose it like that because, just because the left side of the battery is the positive terminal. You could have the initial charges as negative Q naught, positive Q naught like that, but the battery would need to simply overcome the negatives and make the left side positive. So I just assigned them to have the same sign which they will have at the end, okay? And if this discussion is confusing you don't worry, it is not that important. So we start at this point. And we will be traveling around a loop by using Kirchhoff's loop rule. So going from the negative terminal to the positive terminal, we will increase our electric potential by epsilon, and the current is in this direction. Now we will move on a resistor. We are moving along with the current. That's why the voltage will be negative. So we have negative IR. This is by Ohm's law. Then minus the voltage across the capacitor. We know that the Q, the charge of the capacitor, is equal to C times V. So if we solve for V, it's going to be Q over C, as we can see. Q over C. And we are back at where we started. So we get 0. We also know that I, the current, is dq by dt. It is the time derivative of the charge. So I can substitute that. Epsilon, 0. And if you look at this, you will realize something interesting. We have Q and its derivative. This is a differential equation because it has a function and the derivative of that function. And ultimately, we want to solve for this Q, which will be Q of t. We want to solve for it in terms of time. We want to have Q as a function of time, let's say. But how do we proceed? How do we solve this differential equation? Luckily, it is one of the most easiest differential equations that you can encounter. It is a first order separable differential equation. It is first order because the highest derivative is the first derivative of Q. And you will understand why it is separable in a couple of minutes, hopefully. So to continue, I will multiply both sides by C. This is not mandatory, but I just like it when I do it this way, okay? I like to do it this way. RC dq by dt minus Q equaling 0. And so if I continue, what will happen? Well, let's see. So if I do something like this, epsilon C minus Q equaling RC dq by dt. If I do this, I will now do something interesting. First of all, I will put a negative here and change the subtraction on the left side. Q minus epsilon C. The reason I did that is because I want to have the coefficient of Q a positive number. I don't want it to be negative 1. I want it to be a positive 1 because while taking the integral, it will be it will be causing less possibilities for making a mistake. That's the only reason. Okay? And so now I will multiply both sides by dt, and I will divide both sides by Q minus epsilon C and also by RC. If I do that, you will see that we get And also I will toss to negative side, so I will divide by negative RC, let's say. We will have negative dt over RC equaling dq over q minus epsilon c. Alright? Now we are ready to take the integral because we separated the variables. That's where the name separable comes from. On the left we only have t. All other things they are constants. And on the right we only have q, the differential of q and the q itself. That's what we mean by separable. Okay? And whenever you can separate the variables, you can just take the integral on both sides. So the left is obvious. It is from 0 to time t, anytime. And on the right, we will start from an initial charge, q naught, and we want to find q at any time. So if we continue it here, the left side will be negative t over rc. The boundaries, they are very easy to evaluate. When we plug in 0, we get 0. So this is what we are left with. This is going to be equal to, on the right, we will have ln, absolute value q minus epsilon c, and the boundaries. Now, maybe you are surprised that this is the result of the integral. And if you're not convinced, let's say, you can just take the derivative of this. What is the derivative of ln q minus epsilon c? It is just 1 over q minus epsilon c. So it is in fact correct. Okay? And so if we plug in the boundaries on the right, then it's going to be negative trc ln q minus epsilon c, and let me even put the time, yep, minus ln q naught minus epsilon c. Now, it is a property of logarithms that if you have the same base and there is a subtraction, you can combine them under one logarithm as division. So you can write ln q of t minus epsilon c over q naught minus epsilon c. And I can put normal parentheses here because, look at this. Epsilon c is the maximum charge of the capacitor. Because if there is no current, and there will be no current when the capacitor is fully charged, the voltage across will be epsilon. And so Q will be equal to epsilon C, right? That's why it is the maximum charge on the capacitor. Which means that this is either 0 or negative. And clearly this is negative. So we have the division of two negative numbers, which is just positive, which means we can get rid of the absolute value because the absolute value of a positive number is the number itself. And if I raise both sides to the power of e, as the result, I will continue in orange. We have, well, let me write it. We might need some space, but I will try to fit it here. So the result will be Q of t is equal to epsilon c, epsilon c plus Q naught minus epsilon c times e to the power of negative t r c. Alright? And well, is there a better way of writing this? There is. There clearly is. And that is, well, is there though? I'm not sure actually. Maybe there is. I don't know. Let's try this. Q naught e to the power of negative t r c. And then plus epsilon c. Yes, I guess this is better. I guess. It is going to be then 1 minus e to the power of negative t r c. Are these equivalent? Yes, they are equivalent. And just as a check, if we substitute 0 for t, let's see what we get. If we substitute 0, this term gives you q naught. And here, this will be 1. So 1 minus 1 is 0. This term cancels. And we get as the charge at time equals 0, we get Q naught, which is the initial condition that we started with. So this equation is in fact correct. Anyways, I hope this video was helpful. If you have any questions, please write them in the comment section. I hope to see you in another video. Until then, take care.